Can you see it? Yes. I have uploaded here in the platform these slides and also some introductory comments about some of the things that we are going to say today. So it is just more material on the same things that we're going to comment today. And then you go download, if maybe it's going to work. Yes. And it's in PDF, right? See. So here I am. To my personal opinion, usability is one of the less considered topics in design, which is bad for the patient, bad for the engineers, and actually a great field to work in because it is relying on a lot of teamwork. So for usability, you need professionals from very different backgrounds, and it's very stimulating to work in usability of medical devices. Surgeons just love the idea of having a biomedical engineer there for them to make a device easier to use. They just think it's great, and they will be very participative in the design, which is not actually the case when you are trying to solve technical problems. They just want biomedical engineers to solve the problem and come there with a black box. They don't want to know anything about what's in the back or inside the black box. So it's a very challenging field. It has been taken as an important topic for the new regulation in medical devices. So it's going to be mandated by the law, a mandatory test in 2020 in Europe. It is already a mandatory test for design in the FDA regulation, so in the United States. And it is taken into consideration by most international markets, say Japan, China, and things like that. We are going to focus on usability during the design phase, which is what you're doing now. You probably have already gone through the platform, where the platform is telling you which are the standards that you are supposed to be using while designing the medical device. So I am positive you have read the word usability in the standard list. We will try to find a way to interpret the standard in a more scientific way, let's say. And this is probably the only bad news of the whole day. They don't care about what you think. They're just gonna do whatever they think is best, okay? This is what we are doing every single day. We're trying to find a new path because we don't really care about what the designers thought. How should we use the device? Some devices are so easy to be used, there's only one way to use them properly. Take off your glasses and put them back on your face again. There's only one way you can wear your glasses. So design and user experience, they go on the same path sometimes. But other devices, if the interface is complex, well, users, they will just find a way to use the thing in a way they think it's comfortable. And it is a very hands-on approach. They will start touching buttons and going here and there in the interface. The ones of you who ever designed a web app interface know there is no way you can tell the user what he's supposed to be doing. You can either give him just one path, just one button to touch, or they will start touching everything just to see what's going on, okay? So, and this is very bad when we are designing complex medical devices that need the user to follow a strict path. We don't want our users of a extracorporeal circulating machine to try what's going on touching this button if they are not sure what's going to happen, okay? This is a real example. It's a white paper published by the FDA, so by the American government. They opened an observatory study, so they opened actually an office on usability, and they studied people for 4 years just for infusion pumps. You know, they're very silly electromedical devices. They have been there in the market since I was in primary school, and they're just used to regulate the infusion of a drug into the patient circulatory system. They're very, very silly medical devices. They killed 710 people in 5 years just in the United States. It is a small town. 710 people in a coffin. It's a lot of people, okay? Just one device in one country. Medical devices kill people. And you don't want to be the one who designed a killer medical device, okay? You want to be the designer of a life-saving medical device. And these people was killed because the user was taken into a wrong user path by the designers. You see the examples, they were miscalculating the dose of the drug just because they were not reading the difference between a microgram and a milligram. They are supposed to be known what a microgram or a milligram is. They are nurses, okay? They were just not reading. So we don't really want to have another white paper from FDA from another medical device. And that's why we're studying this subject matter today. And I'm pushing this subject matter to become a core subject matter for biomedical engineers. Some other examples. This was information for safe use provided to the patient for a dermal patch. This patch was supposed to be providing a controlled release of drug, and the patient put, instead of understanding their alternate positions, he covered his whole body. Okay, and he got 8 times the dose. So they had to change the information for use and put 8 different pictures to say it's either here, or here, or here, or here, or here, or here, okay? And this is just a silly picture, but it can be actually very dangerous, okay? These patches are very common for contraception, and you don't want a young lady to get 8 times the hormones she's supposed to be needing. It's very bad for her health. More examples. This is a nice way for killing people again. Oxygen through an infusion path. This is this class, there are classes in the web. This is a free class that is provided by the American government for nurses. So on what not to do thing. Do not do this. And then there's something else. We do love our patients sometimes when they don't smell too much. And you really want your patient to be just fine, okay? Your patient deserves to be able to wear a t-shirt and just walk in the street without anyone noticing there is a port in his abdomen. They deserve to be taken into consideration when you're designing a medical device. Because these two devices, they just work the same. There's no difference in the technical performance, okay? But what about patient quality of life? Okay, no more pictures. So from now on, please start taking notes. So what are we studying? We have 3 different levels we want to satisfy. We want our device to be effective. It means it has to work. Remember, we were speaking about safety and performance of the medical device in the previous class. We want our device to work. That's our first aim. You don't really care if a t-shirt is keeping you warm, if it is the coolest t-shirt you have ever bought, right? Sometimes t-shirts are just there to be cool, not to be warm. But medical devices, in the very first thing, they have to work. And then they have to be efficient. Efficient means, I think you know, a good way of using the resources you have. Typically, the most important resource for users is time. So we don't really want our surgeon to manipulate the surgical tool for 10 minutes to understand which is the handle and which is the blade on a surgical field. We want him to grab it and go. So grab it and go, it is a very good hands-on tool to understand if your device is efficient. There are many techniques to understand if the device is efficient time-wise. You can count the use errors, you can count the use uncertainties, you can calculate how many milliseconds the user needs for each task, and it's very interesting. Think about an external defibrillator, one of those in the emergency. You know, those devices, they have some times they really need to have because they are charging the battery before the discharge. And the users have that time to get ready, but if they're slower than that, you're wasting time, right? You're wasting time because the device is ready, but the user is not ready to defibrillate. And then last but not least, the user satisfaction. Of course, if this is a surgical tool and the user is the surgeon, he will have different expectations than a user at home, a little child, or an impaired person, okay? All of these aspects can either increase or decrease safety. So an effective, efficient, and satisfiable device is very safe. This pyramid is taken from a very common book that is used by designers. Of course, our core requirement is always safety. But safety in medical device design goes very strictly with usability because use errors can have bad consequences. And that's why the lower layers of the pyramid are so important for us. And personal perfection and pleasurable experience, well, it depends. Sometimes, if they are web apps that are used by the common user at home, one of those health apps, well, the expectations will be very high. Also, if you want to be a biomedical engineer that is not designing for safety, is designing for bioenhancement, so is designing things to take a healthy body and bring it to a higher performance, then individualism and pleasurable experience is going to be very important for you as well. But not many of you will go in that field, I think. The next generation will go there, not you. So this is a nice little table that comes from the medical device industry standard, the ISO 62340. And it is dividing the medical device use into normal and abnormal. And into the normal use, you find the use error. Because use error is not wanted, is an unwanted consequence of the interaction between the man and the machine. They don't want to make mistakes. Okay? That's why it is considered normal use. That's what you can foresee and prevent. So here is the normal and intended use. Normal and intended use in medical device industry, they go together. They're like twins. Because what you wish your device to do, the performance, is triggering the expected normal use. Sometimes, if normal, okay, let's try to explain it like that. If normal and intended use go into different directions, then the user is working off-label. He's going in a different path than the expected because the designer is going to declare the intended use. And if the user is obeying, then you get a normal use. The wrong use, the use error. So, and here you have some examples of the root cause of the use error. He doesn't remember. He's not following rules. He learned, but he cannot use his knowledge on the situation, so he's just improvising. Oh, the battery is very low. Let's touch this and this and this to see if we can save energy. It's a very typical example, okay? Or he gets information and he does not understand this information. He's putting the information in a wrong place in his brain, which is typically what, if I read and I think I know the unit of measure, typical example of the nurses we were talking about earlier today, they read and they think the patient weight is in pounds instead of it's in kilos and vice versa. So they're putting the correct information in a wrong pattern, okay? The bad use is terrorism. Terrorism in medical devices. They know they are wrong and they don't care, they just do it anyways. They use a sterile device 2 times on 2 different patients. I have seen this done. Okay, I have seen a dentist take a failed dental implant, failed for infection, brush it, throw it in the autoclave, and put it on the next patient. This is a horrible thing to do, don't you think? I have seen nurses cutting the end of a nasogastric tube to avoid having a check valve at the end, having just the open tube, and using this for washing the inside of the stomach of the patient, 2 different tubes. One goes in and the other one goes out. They call it They have a nice name for this procedure. It's like pressure release procedure. It is a horrible thing to do. And there are so many examples. I have seen doctors take sterile Band-Aids and cut it in half, one for one patient and the second half for the next patient. Let's save money. So all these it's terrorism, okay? We really can't foresee terrorism over the normal state of the art. It's very difficult. Some examples here: conscious disregard of counterindications. Do not use if the package is broken, and they use it all the same. Sabotage is what I told you. Or taking an electromedical device and just playing with the plugs because you don't have the, how do you call it, the earth? So they cut the electrical cable and they connect the electrical cable here and there where they find a way, and they don't really think about insulation and things like that. So sabotage. Ignoring the output limit. An alarm is ringing, I just silence it and I go on with my work. I have seen done again with plasma freezers. Plasma freezers, they start ringing at minus 40 degrees because plasma must be kept in a very cold environment, lower than minus 40, and they just go, oh, shut up, you thing. If it melts, I'm gonna see it. As long as it's hard, it's frozen. So you don't really want your user to go, oh, shut up, you thing, to your alarm, right? And the right use is the only way they can use the device according to your specifications. Off-label may not be use error if there is no other solution. So there are so many ways the doctors can use the device in a non-intended way that is beneficial for the patient just because that's the only thing they have. And it should be foreseen and allowed. So from now on, we are trying to see who are the participants, okay, to this design team. So the people and the machine, actually. There are just two big groups. But see, interaction between man and machine can be very different. This little picture here is a standard operating room in Europe. There are thousands and millions of buttons to be pushed, and blinks to be heard, and changing screens to be interpreted. And all this is made by a nurse who is actually called the lady of the iron. In Italian, she's la ferrista. Okay? So the human-machine interaction or interface can be very complex in our world, which is just nice. But also the handle of a crutch is human-machine interface. Okay? So it can also be very, very easy. This is the interface, and this is the interface, if we are talking about glasses. So it's just nice to see there are so many ways you can interact with the machine or with the device. And the people, the intended user, is either the patient or the medical professional or the caregiver. There are so many intended users out there. It depends on the device you're designing. But thanks God, you can sum them up and put them all together in groups. They are easier to be studied when you can herd them in groups and describe the general characteristics of that group. So each surgeon will have his own way of doing things, but okay, trained surgeons are a group. Each mother will have her own way to take the temperature to the little girl that is crying because she has a fever. But okay, mothers can be just grouped together. They have common features, okay? The most important thing to understand is that the patient is not always the user. Sometimes they're very far away. Think telemedicine. The patient can be actually in another continent. So the standard is just dividing these two huge mega groups, patients and users. And see here, in the users, you have so many people you didn't really think about, right? Cleaners, maintenance people, transport people. They're very important as well. You don't want the gentleman that is downloading your device from the van either to be squashed by the device because it tilts while you move it, or to damage your device because he's grabbing a handle that is supposed to be grabbed only in a sterile field. So you have to make sure you take into consideration the expectations of all these user groups. Typically, in complex interfaces, you have different passwords. Admin, user, master, slave. Is it clear why? Because there are different groups. The admin and the users are different user groups. There's a theory behind this, but just to let you know. And more. So for example, you have different user profiles in a software interface. The same medical app can be accessed by the patient and by his physician, and they're gonna see different interfaces to be able to comment the same data. Maybe the patient needs to tell you what happened during that monitoring period. I was walking upstairs, I was running, and that's why you see my heartbeat variation. And the doctor wants to comment in a completely different way because he wants to comment the rhythm or, I don't know, whatever. Okay, so same information, different comments, for example. And here are some examples of device users in our field. Okay, there is a very nice, interesting little example here, the reprocessor. So many times out there, the nurses in the hospital will disassemble the device, wash it, clean it, sterilize it, and assemble it again for the next patient. Think about electrosurgery. Okay, so the handle is washed and reused. Think about endoscopes. So those reprocessing people, why are you watching me like that? You, it's like, okay. I know it's sort of disgusting, the reprocessing of an endoscope is sort of disgusting, I agree. So the user characteristics are very important when you evaluate how to provide them a good user interface. People with a good medical literacy will understand the word sterile, do not use 2 times. So people that are young and have a very good eyesight will be able to see small differences in a small screen and follow the information, read the small characters, or see the small variation in a graph. But that same person, while he's walking, he will not be. Have you ever tried reading a long text while you were walking on your mobile phone? It's so difficult. But then you just need to stop and read, right? So you have to learn those expectations because sometimes they are just on the go. Think about an emergency device. They're just running with the patient and they need to read this graph to see if this patient's heart is beating or not. So physical, sensory, and cognitive characteristics of each user group are very interesting for you to know. And of course, the level of training. Are they using the Da Vinci on the very first day they are employed in the hospital, or do they have a 2 years program to be allowed to touch the Da Vinci? And what about a stethoscope? Who of you is designing the stethoscope? There's a group designing a stethoscope, right? So there's no training for a stethoscope. You just give the stethoscope and they just grab it and go. Do you think your user will go and sit with the seller of the stethoscope? And do you think the user will go and sit with the pharmacist or wherever place he's gonna buy the stethoscope and be trained on the stethoscope? I don't think so. Will they read the instruction manual? Or they will just open the box and start chick, 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 chick? That's what they're gonna look for a nice little icon for switching it on, and they will push that, even if they are perfectly aware that there is no battery, just to see what happens. Because this is what we do, right? When you buy a new telephone, you just want to switch it on. And then maybe you will put it, charge it, and possibly read the instruction manual, but the very first thing is that you touch. This is just human, okay? That's the way we are, we have evolved. So we are describing the user profile. Is he sitting or standing? Is he smart or not? Is he trained or not? Can he see properly? Is he really willingly to use this device, or are we forcing him? Is he bored? Will he focus on the device or not? There is a very big difference of your attention span if you are purchasing a boring thing like toilet paper in the Amazon, or if you're choosing the flight for your next vacation. And for the user, this is the same. Is he using the interface for a pivotal diagnosis in the patient life, or is he just putting the data of the patient age and weight and fiscal code and social security number into the system? What is the probability of a mistake in both situations? And maybe it's the same user with the same interface, with the same patient. So willingness and motivation are very important. If you think the motivation of your user is very low, give him small and short tasks to perform, or he will just go away. Health state, mostly if the user and the patient are the same person. We spoke about this a bit. And this is my favorite slide ever. This is my core slide of the day. Do you agree with me? This is the same technology. There's nothing different. But have you ever tried to take a temperature to a screaming baby? I have. It's so difficult. So thank you, biomedical engineer who thought about putting a thermometer in a pacifier. What is the difference in patient life in this? It's just great. And if you can do this with a glucometer, with a port for insulin infusion, you're going to change a child's life just by designing the interface. There's nothing technologically different in here. So if you are able to go with the wow effect on a device that is actually changing people's lives because you get a screaming infant to a non-screaming and pacified infant, well, you're great biomedical engineers, I think. Let's go on. This is the same machine with two different users. This gentleman here, he really wants to know, number one, how long is this going to take today? Number two, please don't make it yell and blink and sound alarms every 2 minutes because I'm trying to sleep. And this other gentleman here, instead, he needs a lot of information from the machine. And he needs to be told if there's something wrong with the patient, okay? So the different user profiles for the same moment of use of the machine. Of course, oh, sorry. I'm going to leave it there. Safer. The different user environments, we spoke about this a bit. So are we at home? Are we in the hospital? Are we running or are we in an emergency helicopter? It's going to change a lot, okay? So if you want to be a good biomedical engineer, the very first thing you have to say is to define the boundaries of your design. Where is the space? What are you trying to comply with? So again, same thing. We are taking the pressure, okay, blood pressure. But at home, in a non-intensive hospital setting, and in the ICU. It is such a different environment for the same parameter. So here comes the boring part. So I will not comment this, read it if you have time. I think it is very nice to be able to understand that the difference between humans and machines is that humans sometimes they are not consistent, okay? They react in different ways to the same inputs because they're tired, because they're bored, because they are in a hurry, because they want the information or they don't, it was a bad news. So this red part here is what we are designing as usability biomedical engineers. And there are all the parts where the device and the person are interacting. Buttons, screens, handles, the shape of the device, the color, the weight, everything. Is it soft? Is it hard? Is it rough? I will not just comment the slide because it's very simple. After you have made this little creative work, you will have to start describing the interface. So what are we doing? Which is the first button we have to push, and which one is the second button? There is a very nice article out there in PubMed where they divided the interaction between the person and the glucometer into 54 different steps. Of course, it is literature, but it is actually very complex, okay? Even the use of very silly medical device. Think a Band-Aid. How many actions are you going to perform? If you had to make a flowchart of how to put a Band-Aid on a little scratch, it is a nice example, because actually you can divide the action in sub-actions, and for each of them, you have to provide a good user interface to the person. And then you can go on, and what happens when I wash my hands with the Band-Aid, and what happens when I have to take away the Band-Aid, and things like that. So general consideration, try to be consistent with the expectations, okay? The switch on, switch off button is always bright. It typically has a very recognizable icon, and it is in the front part of the device. Everyone is going to watch there. If there is a tank full of water, you are going to be looking for a tap, right? If you see water, you're going to look, where does it come from? Where is it supposed to be going? Because it is consistent with your expectations. If you have a device with a screen, you think you have to push the screen, right? It is consistent with your expectations. Little children, 2, 3 years old, when they watch TV, they touch the screen because they think they can change the people in the screen because they think it's a touch screen. I told to my son, pick up the phone. And he had one of those very traditional phones with a handle, and he gave me the whole machine because the pick up the phone was not clear to him. He didn't know the handle was for answering. But if you say the same sentence to a 75-year-old person, he's going to be, or she is going to be very confused if there is no handle in the phone. They want a handle. Showers. The first time you go in a shower in a hotel, the very first thing you do is like, hot, cold, hot, cold. It is very confusing if it is hot, cold, right? And devices are just the same. They have to be consistent with everyone else's expectation in real life. That's why you make sensorized t-shirts and not sensorized coats or sensorized ball gowns, okay? So here you have some hardware examples, including the packaging and the labeling, okay? Think about a surgical kit. The order of the tools in the surgical kit is a usable interface or a very confusing interface. Can be both. Double pouches for protecting the sterile condition of a sterile medical device can be a good interface or a very confusing interface if they are transparent or opaque. So here there are some to me, very nice examples. My favorite is this at the bottom. It's a centrifuge for separating plasma from the particulate part of the blood. And the shape of the cup, these purple ones, it's proprietary. So the user cannot mix up cups in this brand and cups from another company. They made a proprietary shape because they wanted to force the users to buy their spare parts. Color coding, okay. Red and blue, venous and arterial, very easy. And here, there is a cover on top of the rotating pump to protect the fingers of the person, but it is transparent because they want to see if there is blood circulating, okay? So it is both protection and information in the same little part of plastic. Software examples? You are much more modern than me, so you know much more about interface and software. So I will not I will go fast through here just to let you know. This one is an interface that I participated in the design. This web app is for helping children to adhere to an aerosol therapy. It is a device on the market. And it was a lot of fun to decide if the children were going to have stars or crowns, if they remembered properly when to take the medication. This is actually a device on the market that was developed according to usability principles from the very beginning by a startup company in Milan. So When you design, you have to decide which is the primary operating function and focus there as much as possible, because we have given lots of different examples, but the device, as we said, must be safe. That's its core function. So when you test for usability, you are also testing for safety. That's why typically setting alarm-related user controls is core. Last week, I have been testing the blood banks. Alarms were not automatically resetting around the temperature set point. So I was able to set the blood bank at 4 degrees, and the alarms were ringing at 7, the low temperature, and 15, the high temperature. This is a very stupid medical device interface, because if I set a core value, I expect the alarms just to reset in an interval, right? I'm not expecting to be the one who has to force the alarms to go around the core setting. So it was a very stupid mistake in usability, and safety-related mistake in usability. So here are some examples of hazardous situation in the FDA guidelines. Typically, if the environment is not helping me out, if it is too loud, if it is not bright enough, I cannot see what I'm doing, it can be very confusing for the user, and that's the root cause of all those mistakes in the pump, infusion pump situation is just because they were working in an hazardous situation. They were always in a hurry. They were understaffed. So here are some of the inducing factors, things that can make things, characteristics of the medical device that can make things wrong for the patient. I'm not going to read through all of them, you have them. So what are we doing? We are designing for usability, and typically it is not a straight line. We are going through iterations because we are getting better and better at each iteration. We need to observe real users in real life to get smart ideas on how to get our device more usable. So the spiral model is very applicable to this kind of design. For example, it is not applicable to designing for safety. Think about electrical safety. You have just to know how many resistors, how many insulations, how many blah, blah, blah you want to put, right? There is just one way of designing the thing properly. You're not going to have 6, 7 iterations of an electronic board, I hope. So, and this part of the design is called the formative evaluation, because you use information from the real world and information from your evaluations to change the device, to form the device. To do the formative evaluation, the most important technique is the function analysis. So you have to decide what the device is doing by himself or by itself, and what we, the humans, are doing. For example, I want the device to set the alarms in a good interval around my set point. I want to set the set point. I want to decide the set point. Does it make sense to you? So the question is the machine better than the human? And the answer is, it depends. What is the task? What is the function that we are trying to provide to the patient? Sometimes the machine is better than the human, and sometimes not. And here is a table on the International Standard Committee opinion on what is best to be done by a person and what is best to be done by a machine. And they have a nice little thing here. Humans, it's like sometimes there is a nice little thing say sometimes humans will work even if they are partially damaged. Typically, they will work even in a very stressful situation. Sleep-deprived humans work. Power-deprived machines don't work. So let's go on with this. There are lots of examples here. For formative evaluation, so please plan to change your mind. This is the core of the slide, is plan to change your mind. There is no perfect design without testing on the field in this characteristic of usability. So here are some examples taken from the web. Wireframes, paper-based sketches of a user interface. Or concept. This is another device that I participated into the design. It's drop foot orthosis. And the very first drawing was made like that. There's no need of complicated software to understand if we want the orthosis to go on the back of the leg, on the front of the leg, or around the leg. Okay. This is probably something you all did, right? In these days, just sketching. This is another nice little example. Different user profiles for a dialysis machine. This is a very cheap thing to do, okay? It is I think it was cut from polystyrol. So it's probably €5 each. But it's great to be shown to the user. How do you like the screen? And this is yet another example. So different ideas, different prototypes that go into a final device. In this example, the users were let choose where they wanted the handle and where they wanted the screen and the dimension of the screen and things like that. So how do we use the information? How do we collect the information to change our minds? Through user tests. So real users doing real tasks. And here you have the designer saying, oh no, this is not what you're supposed to be doing, right? And this is a very nice example of how users, they just go their own way. So a typical user test has no interaction. This is very good for testing, but very bad for iterations. So I typically prefer to have very interactive user tests at the very early stages of the device, of the design, and repeat the user testing with no interaction at the end of the device, of the design. So usability tests can be done by observing the user, but you have to tell them what to do. So you have to have a clear list of things they have to do, a clear list, a mission. This is a video game, and you have to solve the first word, second word, third word of the video game. Okay, so give them a mission. I want you to use this interface to create a patient profile. I want you to use this interface to retrieve information from yesterday's patient and compare it to today's patient, and things like that. Of course, most of the time is a simulated use condition. It is not ethical to do it on patients if you're not sure of your design. So you try to use mock-ups, you try to use past data, you try to interview the physician, pretending you are a patient. So it is very non-ethical to use patients for this kind of usability tests. Of course, you need to interview and observe all the groups that we decided to have in our design. So if it is patient and caregiver, surgeon and nurse, you have to interview them all. And here are some examples of how many user groups you can think of. This is perfection. I have never tested a medical device in this environment. It is too expensive. You are usually sitting on a desk in a very loud corridor or things like that. So, but of course, in a class, you will get the best solution ever. Very expensive usability testing lab. And please take movies or what you are testing, because there are so many things going on at the same time, and watching the movie 2-3 times will help you to see all the user uncertainties and small errors that he corrected by himself. I'm nearly done. Last 2-3 slides. Other ways, observational. You just walk around the hospital and check what the patients are doing. You sit in a room and you watch how the nurses are walking into and out of the room. You are watching people in the subway and check how they interact with their health app. You are standing in the surgery room and observing the physicians without talking to them, and you're taking notes. Or you ask them questions according to a very strict checklist, and they can just answer yes, no, or 1, 2, 3, 4, 5. And this is very good for statistics. It's wonderful for statistics, and there are some very easy tools out there that are for free you can use for this kind of statistics. One is called the SUS questionnaire, SUS. It's a very nice little thing you can use. And then last but not least, and actually my favorite technique during the early stages of the design, subjective. Just talk with them, because users, they know so many things you don't know. Mostly if they are clinical professionals, they have so many expectations from the perfect medical device, and you don't really know the expectations until you let them talk. And be very interested, and please be very humble. Just tell them, I am a poor biomedical engineer, I live in numbers, please tell me how real life goes, and you will learn so many things, and your device will be so much more effective and pleasurable and safe. And I'm done. Thank you.